We're going to formalize some terminology here. When we are given a differential equation, such as the one here, the general solution is a family of all possible functions. So that was our y equals scenario. But it'll have some constants that are undetermined in it usually. We'll see how that plays out through examples. Once we have a general solution, we might narrow it down to a particular or a unique solution or a specific solution that satisfies the differential equation. So this is a singleton versus a family of solutions. And we'll see how those arise naturally in solving differential equations. Our first differential equation that we're going to solve the long way is going to be dy dx equals 1 over x squared minus 1. And it's very important to note what variable we're dealing with here. Notice that in this scenario, the variable on the right-hand side is the independent or the variable in the denominator of our derivative here. That means we can simply integrate both sides. If we integrate dy dx with respect to x, the whole point of doing that integral is to eliminate the derivative, we'll get y. And so what we need to do is also integrate the right-hand side at the same time with respect to x. And that should give us y equals a function here of x. This is where we have to review possibly some of the integration techniques. This would be a classic application of partial fractions. We can decompose that denominator into an x minus 1, x plus 1 pair. And from there, we can separate that using partial fractions into two separate terms. If you've not seen partial fractions before, I recommend that you watch the videos or check out the materials that are provided as an appendix for this week. To perform the partial fraction decomposition of this, we take what we have, the x minus 1, x plus 1, and we note that these are distinct linear factors, which is the simplest possible case for integration with partial fractions. And we can break that down into some number over x minus 1 plus some number b over x plus 1. And our goal then is to find what the values of a and b are, and we do that simply by building a common denominator for both terms. To get that, we multiply top and bottom by the same quantities. That'll give us a common denominator on both sides, and because the numerators have to be the same after that, we end up with a x plus 1 plus b x minus 1 is equal to 1. And you can solve that system of equations for a and b however you like. I like doing the sub in particular values of x. And what we do is carefully choose our x's so that one of these terms gets simple. In this case here, if we let x equal 1, this equation should be true for all x's. If we make x equal 1, it's still true, and it simplifies our equation by giving us one coefficient that is 0. This b coefficient here ends up being 0, so we end up simply with 2a equals 1, or a equals 1/2. And if we do the same thing for x equals negative 1, if we do that a little more briefly, if x is negative 1, this coefficient 0, we end up with b times negative 1 minus 1 equals 1, and b is equal to negative 1/2. Once we've done that identification of the values of a and b, what we can do is rewrite our integral with the, being careful to note what went with what, a over x negative 1, b over x plus 1. So our y is equal to the integral of 1 over x minus 1 times x plus 1. And we just said we could decompose that into a, which is a half, over x minus 1, plus b, which was negative a half, over x, careful, those are backwards, x negative 1, x minus 1, and x plus 1 dx. The decomposition, partial fraction decomposition, lets us break a product into two separate terms, and that makes it easier to integrate. So just a note of the term here. So with that decomposition complete, we can now integrate easily. And when we do that, we end up with 1/2. The x minus 1 here ends up being a ln. And we remember the absolute value appears when we do an integral, which could potentially have negative x values in it. And then we have the -1/2 ln of x plus 1 and plus some constant c, y equals. And that would satisfy this original differential equation. How do we know that? Well, we'll see some techniques later on for verifying, but in this case here, we simply integrated both sides, treated both sides on equal terms, and ended up with y equals a function of x, and so we would arrive at our solution. We note that the plus c here, this indicates that we have a family of solutions. It's a fairly simple family. This plus c would just shift these graphs up and down. And so this would be the general solution in our usual terms. However, we could refine that. We have the same differential equation here, but if we add the extra condition that the value of y has to be 1 when x equals 2, let's be clear about the relationship, x equals 2, y equals 1, what that'll let us do is narrow down to a single, or what we call a particular, solution. And that's equivalent in our case to finding the value of c. That was in the general solution. If we could pick c however we wanted, then there'd be lots of choices for functions, but if we have to go through this one point, there's probably only one choice that'll work. So we include our values here from before, the general solution, which had a -1/2 next, and ln of x plus 1 plus c, and then we simply take the values that we know we have to satisfy and use those in our equation. So the y value has to be 1, and the x value has to be 2, so we'll put that in a second in a different color. 2 for x, 2 for x. Finish the absolute values. And the one value that's not determined is c. And then it just becomes an exercise in moving pieces around. So we have 1 equals 1/2 ln of 2 minus 1. Let's simplify our lives right now. This is ln of 1, but ln of 1 fortunately is equal to 0, so this whole term goes away. And then we're simply left with this term here, which we would add to the other side. So we'd have 1 plus 1/2 ln of 3. Don't need the absolute values, it's positive 3. That equals our constant c. So y equals 1/2 ln absolute x minus 1 minus 1/2 ln of x plus 1, absolute values, plus, let's put this on the next line, 1 plus 1/2 ln of 3. That would be a particular solution to the same differential equation, but that satisfies the condition that y of 2 must equal 1, as well as, again, the differential equation. And so that's the distinction between a particular solution, which is a simple formula we could graph, versus the general solution, which was or had some undetermined value in it that could be chosen however we liked. It wasn't dictated by the differential equation itself.